The Circinus Galaxy, located approximately 13 million light-years from Earth, is home to a supermassive black hole, one of the many scattered across the cosmos. As one of the closest active galactic nuclei to our planet, it offers a unique opportunity to study the intricate mechanisms surrounding these mysterious cosmic entities. The research conducted on Circinus is vital for understanding the processes that drive black hole activity, their growth, and the overall dynamics of the surrounding galaxy. For decades, astronomers have been observing this galaxy, trying to unravel the puzzle of how the supermassive black hole interacts with its environment, and how its accretion disk and outflows influence the galaxy's evolution. At the heart of this research is the black hole's effect on the surrounding material. One of the main sources of infrared light emitted by the Circinus Galaxy has been the outflows, streams of superheated matter that are ejected from the region around the black hole. These outflows were once believed to be the largest contributors to the observed infrared emissions. However, this long-standing belief has now been challenged by new observations from NASA's James Webb Space Telescope (JWST), which, in combination with data from NASA's Hubble Space Telescope, has provided fresh insights into the matter. The JWST's advanced infrared capabilities have revealed a different perspective, suggesting that the majority of the hot, dusty material observed around the black hole is actually being accreted into the black hole itself. This discovery shifts the focus of scientific research from outflows to the accretion process, where matter is pulled into the black hole rather than expelled. By observing the infrared emissions, the scientists were able to distinguish the components of the black hole's environment with a degree of precision never before achieved. This breakthrough observation is not only critical for understanding the Circinus Galaxy, but also opens new avenues for studying similar systems in other galaxies across the universe. This new data significantly alters the existing models of the Circinus Galaxy, which had long been shaped by the assumption that outflows were the primary source of the galaxy's infrared radiation. For years, astronomers had worked with models that attempted to fit spectral data from different regions around the black hole. These models were based on identifying emissions from the accretion disk, the torus of material surrounding the black hole, and the outflows. However, these models were incomplete, as they lacked the ability to resolve the detailed structure of the galaxy's center, especially when it came to pinpointing the origin of the excess infrared emissions. One of the major hurdles astronomers faced when studying the Circinus Galaxy was the overwhelming brightness of the surrounding stars, which obscured the inner workings of the black hole. This starlight made it difficult for ground-based telescopes to see through to the faint infrared emissions coming from the immediate vicinity of the black hole. Furthermore, the torus, a dense ring of gas and dust surrounding the black hole, obscured the inner region of the accretion disk, making it even more challenging to study the black hole's activity. For decades, astronomers had been unable to overcome these challenges, and many of the details about the galaxy's center remained shrouded in mystery. In their earlier attempts to model the behavior of Circinus, astronomers focused on specific emission lines, those corresponding to the torus, the accretion disk, and the outflows. These lines, detectable at specific wavelengths, allowed scientists to make educated guesses about the galaxy's structure. However, many of these models struggled to explain certain observations, particularly the excess infrared light that was detected from the core of the galaxy. This light was too intense to be explained solely by the outflows or the torus, leaving a gap in the scientific understanding of what was happening in the center of Circinus. The breakthrough came when researchers turned to the James Webb Space Telescope, which boasts unprecedented sensitivity and resolution in the infrared spectrum. One of Webb's key features is its ability to isolate specific wavelengths of light, filtering out the starlight that previously hindered observations. This was essential for allowing scientists to see through the dense clouds of gas and dust surrounding the black hole. Additionally, Webb's sophisticated technology allowed the team to distinguish between emissions from the torus and the outflows, offering a much clearer picture of what was occurring in the galaxy's heart. In order to gather the data, the team used a specialized instrument on Webb, the Aperture Masking Interferometer, (AMI), which was able to produce highly detailed images of the galaxy's core. This tool uses a unique set of hexagonal holes to create interference patterns in the light it gathers, effectively allowing Webb to act as an array of smaller telescopes working together. This method of combining the light from multiple apertures increases the resolution of the telescope, allowing scientists to observe the center of Circinus with extraordinary clarity. In essence, Webb's AMI mode allowed astronomers to see features of the black hole's environment with a resolving power equivalent to a 13-meter telescope, twice the size of Webb's primary mirror. When the data was processed and analyzed, the results were astounding. The new images and spectral data showed that, contrary to earlier models, the vast majority of the infrared emissions from Circinus were coming from hot dust located close to the black hole, around 87% of the observed emissions. This finding significantly diminishes the role of outflows, which were previously thought to account for most of the infrared radiation. In fact, less than 1% of the infrared emissions were traced back to the outflows, appending the conventional wisdom that had dominated scientific understanding for decades. This discovery also sheds light on the process by which supermassive black holes feed. The accretion disk, which forms as gas and dust are drawn toward the black hole, is known to emit intense radiation due to the friction and heat generated as the material spirals inward. This process causes the disk to glow brightly, emitting electromagnetic radiation across the entire spectrum, from ultraviolet to infrared. The hot dust near the black hole, which contributes significantly to the infrared emissions, is likely the product of this intense heating within the accretion disk. This dust is not merely being ejected as part of an outflow, but rather as part of the matter being consumed by the black hole, reinforcing the concept of active accretion rather than material being expelled outward. This shift in understanding is important not only for the study of the Circinus Galaxy, but also for the broader field of extragalactic astronomy. The techniques and technologies used to observe Circinus can now be applied to other galaxies with active supermassive black holes. The ability to distinguish between accretion and outflow components in the infrared spectrum opens up new avenues for studying the feeding mechanisms of black holes in distant galaxies. In particular, this method could prove invaluable in analyzing other galaxies whose centers are similarly obscured by dense clouds of gas and dust. The implications of this research are far-reaching. For one, it challenges the previously held notion that outflows are the dominant feature of a black hole's environment, especially in galaxies with active nuclei. Instead, the focus is now on the accretion process, which is responsible for much of the energy and material that fuels the black hole's growth. Furthermore, the success of Webb's AMI tool in observing Circinus demonstrates the power of next-generation space telescopes in resolving the most elusive and distant regions of the universe. Webb's unprecedented resolution and sensitivity are poised to revolutionize our understanding of supermassive black holes, their role in galactic evolution, and the intricate dynamics of matter under extreme conditions. In addition to the immediate scientific breakthroughs, the research also provides valuable insights into the future of astronomical instrumentation. The use of aperture masking interferometry in space is a cutting-edge technique that will undoubtedly influence the design of future telescopes. By combining the capabilities of multiple smaller apertures, Webb was able to achieve a level of detail that would have been impossible with traditional single-aperture telescopes. This approach opens up new possibilities for observing distant and faint objects, from active galactic nuclei to exoplanets and beyond. Moreover, the study of the Circinus Galaxy and its supermassive black hole serves as a reminder of the immense challenges that astronomers face when trying to study the universe's most extreme environments. The dust, gas, and radiation surrounding a black hole can obscure our view, and only the most advanced instruments, like the James Webb Space Telescope, are capable of peering through these cosmic barriers. The insights gained from this research not only refine our understanding of black holes, but also provide a blueprint for future studies of similar systems in galaxies far beyond our reach. In conclusion, the new findings on the Circinus Galaxy highlight the importance of next-generation space telescopes in unraveling the mysteries of supermassive black holes and their environments. The role of accretion, as opposed to outflows, in producing the galaxy's infrared emissions marks a significant shift in our understanding of black hole activity. This breakthrough offers a glimpse into the future of extragalactic astronomy, where the combination of innovative techniques, advanced instruments, and detailed observations will continue to reshape our view of the universe's most enigmatic objects.